Hello, my name is Tyler Ehrlich. I'm part of Group 3, and I'll be doing the first part of Project 5. I'll be talking about insulators, semiconductors, and conductors. All three of these have to do with the flow of electricity. To explain these three, I will talk about them like they're people walking on a path. A conductor is like an open road with no obstacles or anything blocking. This allows you to just walk freely across it. Certain metals that are like this are copper and aluminum. Another way that this could be thought about is like water flowing down a river, and nothing is stopping its flow. For insulators, however, it is the exact opposite. You can think of it as a narrow path that is blocked by trees and rocks, and it's just incredibly hard to walk across. This would not allow you to pass, which is what it does with electricity. Some things that insulate are rubbers and plastics. For example, going back to the river, it's like someone put a dam to stop the flow of the water. Semiconductors are a bit trickier though. It's not quite all the way open, but it's also not closed. It's somewhere in the middle. It can be thought of as a road that needs to have a gate open for you to pass. These allow us to control the flow whether or not electricity is able to enter, just like if you're able to pass the gate by it being open or closed.
Hello, my name is Andrew Horn, and I'm also part of Group 3. I will be explaining the three types of primary bonds, temporary and permanent dipole interactions, hydrogen bonds, energy bands, band gap theory, and I will also be explaining how the results of the lab we performed show that resistance is equal to rho, which is the resistivity of the used material multiplied by length and divided by the cross-sectional area of the material. The three types of primary bonds are covalent bonds, ionic bonds, and metallic bonds. Bonds form because atoms act to become more stable. Covalent bonds are bonds between two atoms where they share electrons to have fully filled outermost shells, which is a more stable state than having a partially filled outer shell. Materials with covalent bonds are usually semiconductors. Ionic bonds occur when two atoms permanently transfer electrons to fully empty one of the atom's outer shells and fully fill one of the other atom's atom shells. This creates a cation and an anion. The cation is the atom that loses an electron, and the anion is the atom that gains the electron. Materials with ionic bonds are usually insulators, due to electron transfer being difficult. Metallic bonds are when all of the valence electrons of a material are shared by all the atoms in the material. Materials with metallic bonds are usually conductors, due to electrons being more free to take part in charge transfer. Secondary bonds, also called van der Waals bonds, occur due to dipole interactions, of which there are two types, permanent and temporary. Permanent dipoles are when the positive and negative sides of two molecules are bonded. Hydrogen bonds are an example of this. Temporary dipoles occur when the electron clouds of two atoms become asymmetrically charged for very brief periods of time, attracting the molecules together. Secondary bonds are generally weaker than primary bonds. Band gap theory is the idea that when multiple atoms are bonded together, the energy states of their electrons, which would normally be equal when not bonded, become slightly different, creating bands of similar but slightly different energy states, with there being gaps between them, generally preferring lower energy states. Additionally, the level at which these bands are occupied and the size of the gap between them relates to the conductivity of a material. Small band gaps are common in semiconductor materials. Large band gaps are common in insulators, and if a material has no band gap, it is often a conductor. Resistivity is proportional to the length of the area multiplied by the resistivity of the material, designated by the symbol rho, divided by the cross-sectional area of the material. In the lab experiment we performed, it showed this relationship to be true, as when we used a potentiometer across a resistor, it had a linear relationship between the distance between the potentiometer and the end of the resistor. Because the material is constant and so is the cross-sectional area, this proves that R equals rho times length divided by area, cross-sectional area.
For question number 3, I'll be talking about the conduction electrons and holes, as well as mobility of intrinsic and extrinsic semiconductors. In a semiconductor, some electrons can break free and start to move around. These allow for electricity to be produced. For example, imagine if you were an electron and we shove you and 40 other people in a small room. There is no room to walk around or to get to the other side. At this point, there would be no transfer of electrons, causing no electricity because you cannot move. Now imagine if we pull 20 people out of the room and make it significantly easier to walk from one side to the other. This movement allows for the transfer of electrons because you're able to walk freely from one side to the next. However, for the conduction of holes, imagine that there is no one at all in the room. Since there is no one in the room, there will be no electrons, or in this case, people moving back and forth. Therefore, the transfer of electrons is not possible. Mobility talks about how easily electrons can move through certain materials. For high mobility, they move quickly, jumping back and forth, but with slow mobility, they move slow and could be obstructed. Two materials to talk about are germanium and silicon. Germanium has less control of its electrons in its orbital, which will result in electrons moving more freely than in silicon. For example, if you have the same amount of people in a large room and a small room, it will be much easier for those people to move around in the large room than it will be for them to move in the small room. Extrinsic semiconductors need to be doped because they do not naturally have electrons in their conduction band. However, intrinsic semiconductors do not need to be doped. For the second part, I'll be talking about why pure gallium phosphide emits green light. This is because of the fact that it has a larger band gap, resulting in higher energy photons, which in turn produces the green light. For the other part of gallium arsenide, it has a smaller band gap, causing lower energy photons, which then causes the infrared light.
Hello, my name is Liam Mosier, and I am a member of Group 3. Today I'll be talking about Part 4 of the project. First, for our mobilities for our semiconductor silicon, we have 0.85 meters squared per volt second and 0.45 meters squared per volt second for mobility for electrons and holes respectively. Our intrinsic concentration is going to be 1.3 times 10 to the 16 per meters cubed. The reason we are able to use intrinsic concentration is because we have an undoped silicon semiconductor, meaning that our concentration for electrons and our concentration for holes will be the exact same. Therefore, we can just use an intrinsic concentration. For our conductivity at 300 degrees Kelvin, we use the formula, our conductivity equals to elementary charge times the intrinsic concentration times mobility of electrons plus holes. From this, we've gathered that we have a conductivity of 2.7 times 10 to the 3 per ohm meter. For our resistor, we have a length of 1 centimeter and a cross-sectional area of 1 millimeter squared, which converted into meters, which we will use for this equation, is 10 to the negative 2 meters for our length and 10 to the negative 6 meters squared for our cross-sectional area. Our resistance formula is equal to resistivity times the length over the cross-sectional area, which, because our conductivity is equal to 1 over the resistance, we can change to length over the conductivity times cross-sectional area, which from this we get that our resistance for our resistor is 3.7 times 10 to the 6 ohms, which is quite high for a resistor. When the temperature is raised to 700 degrees Kelvin, our intrinsic concentration will change. We can solve for our new intrinsic concentration using this formula. We only need our band gap, which is 1.2 electron volts per silicon, as well as the Boltzmann constant and the temperatures that we used. For our new intrinsic concentration at 700 degrees, we got 4.2 times 10 to the 27 per meter cubed. Using this, we can get our new conductivity, which is 8.7 times 10 to the 8 per ohm meter, which is significantly higher than before. And now, with our resistor, we have 1.1 times 10 to the negative 5 ohms, which is significantly lower than before. For our second part of part 4, we have our silicon doped with 2 times 10 to the 19 per centimeter cubed boron atoms, which will end up being a p-type doping, as it will introduce more holes into the silicon. We will convert this unit into meters per meters cubed, and we will get 2 times 10 to the 25 per meters cubed for P, which is our concentration of holes. We can no longer use our intrinsic concentration in our formula for conductivity due to us having a doped silicon semiconductor. But we can solve for N and P because we already have P here. But we can solve for N using N times P equals Ni squared. We know the intrinsic concentration as well as our P concentration. So if we convert this into N equals Ni squared over P, we can find our concentration of electrons, which will end up being 8.5 times 10 to the 6 per meters cubed. Now we can solve for our conductivity using the formula before, but we change our intrinsic concentration to a concentration of electrons and concentration of holes. We end up getting our concentration is equal to our elementary charge times the mobility of electrons times concentration of electrons plus mobility of holes times concentration of holes. Using this, we have a conductivity of 1.4 times 10 to the 6 per ohm meter in our silicon resistor. Using this, we can get a resistance in our resistor of 7.1 times 10 to the negative 3 ohms, which is significantly lower than when it was not doped and at the same temperature, showing that doping will reduce our resistance. When we raise the temperature to 700 degrees Kelvin, we will now have a new intrinsic concentration, which is the same as before when we had a temperature raised to 700 degrees Kelvin, which is 4.2 times 10 to the 27 per meters cubed. We can now solve for a new concentration of electrons, which is now 8.8 times 10 to the 29 per meters cubed. Because of this, we now have a new conductivity, which we have solved for to find that it is 1.2 times 10 to the 11 per ohm meter. And now we can solve for a resistor, which now has a resistance of 8.3 times 10 to the negative 8 ohms, which is significantly lower than anything before.